It has been mentioned previously that this course is about the study of operation and performance of power electronic converters. We have also listed a few ways to determine the performance of a power converter. One of the ways to determine the performance of a power converter is the waveform quality. That is, to see whether the voltage and current waveforms are close to the ideal case or not, and how close they are, what are the desirable and undesirable components of these waveforms, and how do they compare against each other. We have also defined certain measures to quantify the waveforms in that process. These waveform measures can give us a quantitative assessment of the performance of a power converter. Another way to look at the performance of a power converter is in terms of the energy lost in the power converter or power loss. This will help us determine the efficiency of power conversion. Ideally, we would like to have 100% efficiency, but any real power electronic converter will have efficiency less than that. What is the reason behind that? What are the contributors to the power loss in a power converter? Obviously, the constituent elements of the power converter. And what are those elements? Switches, inductors, and capacitors. The non-ideal behavior of these circuit elements is the cause of power loss in a power converter. Once we understand the ideal behavior of the circuit elements, we will be able to appreciate the effects of non-ideal behavior. So, let us try to answer this question. How should the circuit elements of a power electronic converter, behave ideally? Or what are the ideal characteristics of the circuit elements? We know that a switch is the most essential circuit element in a power electronic converter. Let us try to understand what a switch does in a power electronic converter so that we can define its characteristics. Let us consider the first circuit shown here in blue color. We have a DC voltage source 200 volts and there is a switch and that is connected to a resistor. The value of resistance is 10 ohms and all three elements are connected in series. So let us see the voltage and current defined for the switch. So the current flowing through the switch and the voltage across the switch. The current flowing through the switch is denoted by Is and the voltage across the switch is denoted by Vs here. So when the switch S is on, the current that flows in this circuit is 20 ampere and the switch should be capable of carrying that current. And what is the voltage across the switch when it is on? There should not be any voltage drop across the switch ideally. And when the switch is off, there is no current in the circuit and the voltage across the switch will be now equal to the input voltage. If you apply KVL, Vs will be equal to 200 volts. So the switch should withstand this voltage of 200 volts when it is off. And how does that happen? It can happen if there is an electric field within the switch which opposes this 200 volts and the potential difference in that electric field is negative of 200 volts. So there won't be any current flowing in the circuit in the off state when the switch is in off state. Similarly, in the on state, how can a switch carry current? There should be some medium for the flow of electrons and the current density in that medium should be such that the external circuit can pump 20 amperes of current. It is important to note that the current carrying capability and the voltage withstanding capability, the current carrying capability corresponding to the on state and the voltage withstanding capability corresponding to the off state of a switch are decided by the external circuit in which it is connected. For example, you consider the second circuit drawn in purple color where the DC source is replaced by AC source. So we have an AC source whose peak magnitude is 200 volts and frequency is 50 Hz. Again, in this circuit we have the same resistance, 10 ohm resistance. When the switch S is on, the current in this circuit could be positive or negative depending on the time instant, and it could be varying from all the way 0 to 20 ampere. That means here in this case the switch should be capable of carrying current in both directions. So that is called bidirectional current carrying capability. Either positive current or negative current should flow through the switch. And of course the voltage across the switch should be 0 as we desire in the on state. If you look at the off state, in the off state again the current should be 0, but the voltage across the switch could be anything between 0 to 200 volts, either positive or negative. It depends on the time instant, because our input voltage is now an AC voltage which has positive and negative values. So we need to have a bidirectional voltage withstanding capability for this switch. With this, let us try to define the characteristics of an ideal switch that is used in power electronic circuit. An ideal switch in the off state, I off, the off state current should be 0 and the off state voltage should be anything. It should be able to block any voltage and the current in the off state should be 0. If there is any current, there will be loss, power loss, because voltage multiplied by current is power loss. So that is called blocking loss, the power lost while blocking. So ideally a switch should not have any blocking loss. Coming to the on state, a switch should be able to carry any amount of current while it is on, and it should not have any voltage drop across that. That means V on should be 0. What happens if V on is finite? V on multiplied by I on will be finite. That means there will be conduction loss. There will be some power loss during conduction. So an ideal switch will not have any conduction loss. Then let us try to bring in time. The switch should be able to change its state instantaneously, or the time taken for transition from one state to the other should be 0. Here the time taken for the transition from on state to off state is denoted by T on with an arrow off. T on to off is 0. Similarly, T off to on should also be 0. So if this is not the case, then there will be again power loss, which is called switching loss. We'll learn about that soon. And an ideal switch does not need energy to switch on or off, or to be maintained in the on or off states. This is called as zero control effort, and the switch should be stable in all ambient conditions. So it should be indestructible ideally. But practical switches have limitations on all the above characteristics. For example, the switches have limited voltage blocking and current carrying capabilities. These are called voltage ratings and current ratings of switches. And the states of a switch cannot be changed instantaneously. For example, a switch which was on cannot instantaneously turn off. It needs some time to turn off. So there are finite times for state transition. These are called turn on time and turn off times. And some of the switches do need energy to be maintained in one particular state, on state, and most of the switches need energy for the initiation of any switching transition. And there will be a specified range of operating temperature for any practical switch, and the practical switches are made of semiconductor materials. Silicon has been a very popular and widely used material to make these power electronic switches. Other materials such as silicon carbide and gallium nitride are being used in recent times to make more efficient switches. The voltage withstanding capability and the current carrying capability of a switch are typically illustrated in VI characteristics, and the VI characteristics of an ideal switch are shown here. In the on state, the characteristic is a green line which is along the current axis. That means the switch can carry any amount of current without having any voltage across it. and in the off state the characteristic is along voltage axis, which indicates that the switch can withstand any voltage, but the current through that will be 0. Now let us consider the other circuit element that is present in power electronic circuits, the inductor. An ideal inductor will be able to carry any amount of current, and there won't be magnetic saturation because inductor is usually made of core and winding. So there won't be any power loss in core and there won't be any power loss in winding, and the inductor will also not have any capacitance. But a practical inductor has limitations on all the above characteristics. For example, a given inductor can only carry certain amount of current, and that is decided by the material of the winding, usually which is copper, and any metal has a specific current density. Beyond that it cannot operate. That means there will be huge temperature rise. So the current carrying capability of an inductor is limited by the current density of the material used to make the winding. Then there will be magnetic saturation once you go beyond a certain current because of the material properties, the core material properties. So typically magnetic materials are used as the core of an inductor. So these magnetic materials have BH characteristic as shown here. So the flux density tends to saturate once the magnetic field intensity goes beyond a certain point, and the magnetic field intensity, whose units are ampere per meter, which is denoted by H, is proportional to the current enclosed as told by Ampere's law, and the flux density is again proportional to the flux cutting across a particular surface. So if we go beyond a certain current, the magnetic field intensity we are trying to increase, but then the flux density does not really increase, it gets saturated. So there will be saturation of inductor. And what do we mean by saturation of an inductor? When the inductor saturates, or when the core of an inductor saturates, the flux density cannot change anymore. So the time derivative of flux density is 0. So the induced EMF is 0. So that with the induced EMF 0, there won't be any voltage across the inductor. That means the inductor behaves like a short circuit and the current has to be limited, otherwise it will get damaged. Coming to the power loss in an inductor, there will be hysteresis loss and eddy current loss in the core. Eddy currents are induced in the core, and hysteresis loss is characterized by the hysteresis loop area, which is specifically given for a magnetic material. As we know, these core losses are functions of the maximum flux density of operation and the rate at which the flux density is changing, number of cycles of flux density per second. The winding of an inductor also contributes to power loss. There will be loss due to its own resistance, which is given by the total RMS current square multiplied by the resistance, and there will be eddy currents within the inductor winding. So these eddy currents are due to skin effect and proximity effect, which are more prominent at high frequencies. That means when the frequency of the current flowing through the winding is high, starting from a few kilohertz, these effects cause eddy currents, which in turn cause additional power loss happening in the winding. So totally there will be power loss in a practical inductor, and the practical inductor will also have certain capacitance. We can define the capacitance between two turns, because there will be insulation around each turn and there will be a little potential difference between two turns. However, the capacitance effects are again dominant at high frequencies, mostly from a few tens of kilohertz and even beyond that. And what are the typical materials that are used for the core of an inductor in power electronic circuit? The materials are amorphous iron, are powdered iron or sandust and molybdenum, that is MPP powder core, or ferrite cores. These are the popular materials used for the core of an inductor in power electronic circuits. The windings are typically made of copper and magnet wire, which is a copper wire with enamel coating, is the most popular wire used to make an inductor, or it could be a leads wire where there are multiple strands of copper and each strand is insulated from the other, and in fact some inductors have PCB traces themselves as the windings, so they are called planar inductors, and some inductors use strips, thick copper strips as an inductor. So different forms of this copper wire are used as the winding in an inductor. Now coming to the third most important element in power electronic circuits, the capacitor. An ideal capacitor should withstand any voltage and there should be no power loss in the capacitor, and there should also be no inductance. And while the practical capacitor has limitations on again all the above characteristics, so it can only withstand certain voltage which is given by the voltage rating of a capacitor, 100 volts, 200 volts, 1000 volts, that is the voltage rating given. There are different types of capacitors that are used in power electronic circuits. The most popular ones are aluminum electrolytic capacitors, and then come the metallized polypropylene capacitors, which are popularly known as film capacitors. They are also made of some certain other polymers, and then the ceramic capacitors. Coming to the practical equivalent circuit of a capacitor, it has all three elements. It has two resistances, the one corresponding to the leakage, R leakage, which is in parallel with the C, and there is something called ESR, which is a very popular parameter given by the capacitor manufacturers, equivalent series resistance, and then there is equivalent series inductance also, which becomes dominant again at high frequencies. This is a typical equivalent circuit of an electrolytic capacitor, aluminum electrolytic capacitor. So what are the contributors to this resistance, equivalent series resistance? So if you look at the capacitor, aluminum electrolytic capacitor, there is a foil which is made of aluminum typically, and then you have an oxide layer, and then there is an electrolyte, and then there is again a foil. So all these materials do have certain limited resistivity, and that contributes to the resistance, and the cumulative effect of all these is given as equivalent series resistance of a capacitor. When there is current flowing through a resistor, there will be power loss. So there will be power loss in this ESR typically, this because the leakage resistance is very negligible. So most of the current flows through the capacitor and the ESR and ESL. So the capacitor RMS current I square multiplied by ESR will give the power loss, and that will cause the temperature rise of the core of a capacitor. So to summarize, all the elements of a power electronic converter, the switches, inductors and capacitors, all of them contribute to the inefficiency of the power converter, as there is a finite power loss associated with each of them. However, the major contribution to loss in most of the power electronic circuits comes from the losses in switches and inductors.